Section 3-4. It's on the definition of derivative as a function. The objective of this section is given the equation of a function. Find the equation of the derivative function. If you recall at the end of the last section there, we were sketching the derivative function. In fact, we were even using the nderiv command to sketch the derivative on our calculator. And the question is, can we actually come up with what the equation of that function is? And so we're going to look at how we can actually do that here. All right. Let's start out with just a little recall here from the last section, actually, on the forward difference quotient. And actually, this will kind of lead us right into that definition that we're looking for how we find the derivative function. And let's just sketch a function here. It really doesn't matter what our function looks like. We'll sketch a function that looks like this. We'll call that f of x. And let's pick a point here. We'll call this x. That corresponds, remember, to the point x, f of x. And then we moved forward some distance. We called that h, to a point here that's called x plus h then. And that corresponds to this point right here, which is the point x plus h, f of x plus h. And then the forward difference quotient was just the slope between those two. Again, it was called the forward difference quotient because from point x we moved forward that distance h. So our forward difference quotient was simply this. Abbreviated that FDQ. It's the slope here. It's the change in y's over the change in x's. So it's f of x plus h minus f of x all over x plus h minus x. And I just put that in parentheses. That in this case it's not too difficult if the denominator is simplified properly, but if it helps you to add parentheses, do so. The numerator stays the same. And here again, remember the x's cancel out in the denominator, so this is all over h. And that right there is our forward difference quotient. And what I want to use that for is I want to take the limit of this formula for slope, this forward difference quotient. And what I'm going to force to happen is I'm going to force this distance h here between these 2 points to get smaller and smaller and smaller. In other words, I'm going to force h to approach a value of 0. And by doing so, in essence, what's going to happen is the distance between these 2 points becomes smaller and smaller and smaller. And thus, I get not just the derivative at a point, but I'll actually get the derivative function when I do that. And the reason for that is you can see that in this forward difference quotient formula, I have both x and h in there. And because of that fact, when I let h go to 0, I'll still have x's in there. I won't come up with just a number anymore to represent the slope at one point, but rather I'll have an equation that represents the slope at every single point. And that's what we're looking for. So that brings us to then our definition of a derivative as a function. And there's actually several different ways that we can see this written. I'm going to start out with the way that we just basically saw there in our forward difference quotient. Again, we're going to define what f prime of x is. This is now a derivative function because of the fact that it's going to find the derivative at every single point. It's going to be a function in terms of x. It gives me an equation. So it's that limit as h goes to 0 of this forward difference quotient, f of x plus h minus f of x all over h. Now, as far as why we use the forward difference quotient, it's just by history and convention that that's what we use. Technically, you could use any one of the 3 difference quotients, the forward, backward, or symmetric, and you get the same result, but by tradition, this is the one we use. So that's what we're going to stick to. Now, that's one way that we can write this. And again, you can see that as I let h go to 0, that I'm going to end up with x's still in that forward difference quotient. And because of the fact that I'll still have x's in there, that's what's going to give me this as a function of x. And it gives me an equation now. All right, other ways that we might see this written, sometimes we replace h with delta x. So instead of calling, let me scroll back up to our graph there, instead of calling that distance between those 2 points h, we might call this delta x. And so let me just label that as delta x is another way that we might mark that distance there. It means the same thing. Okay, of course this point here changes from x plus h to x plus delta x when we do that. And it changes my formula slightly as well because I replace all the h's with delta x's. But that's all we can see, or that's what we can see happens here. If I replace the h with delta x, I have the limit as delta x goes to 0 of f of x plus delta x instead of h minus f of x all over delta x. So that's all we've done. It's basically a substitution of variables. And another way that we might see this written is a limit as delta x goes to y, delta x goes to 0 of delta y over delta x. It's really just measuring a change in y over a change in x is what we see there when we measure f of x plus h minus f of x. That's a change in y. So this is another way that we can write that difference quotient. Most of the time we're going to write it in the first form. There will be some times that we use the delta x instead of h like you see in the second form. And some cases we're going to write it in that last form, but not very often. All right. One last term that we should describe here for us so that we understand what this means, and that is differentiation, or sometimes we call it to differentiate. Differentiation is the process of finding an equation for the derivative of a function. So the book might ask you to use differentiation to find f prime, or they might say differentiate f of x, find f prime of x. Those all mean find the derivative. That's another way that we describe a derivative, differentiation. All right, let's take a look at example 1. And let's put this definition that we just came up with for a derivative to work here. It says given f of x equals x to the 5th. So let's write down that function there. F of x equals x to the 5th. Use the definition of derivative to find an equation for f prime of x. So again, notice that we're not finding the derivative at a single point. They didn't ask us to find the derivative at 2 or the derivative at 5 or at negative 7. They asked us to find the derivative function here. Find the an equation for f prime of x. So that's our derivative function they want. All right, so we're just going to use our definition. This is where you need to start every single time. Just write down the definition that we just had up there. So it's the f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. All right, now it requires a little bit of substitution to simplify this. We've got the limit as h goes to 0. F of x plus h, that means that in my function for f of x, I'm going to replace the x's in there with x plus h. So instead of just x to the 5th, it's going to be the quantity x plus h to the 5th. Okay, that's what f of x plus h is. Minus f of x. F of x is the original function we were given, so that's x to the 5th. And that's all divided by h. Notice we start with the same first step that we did with the other definition that we saw back in section 3.2. Starts out with substitution. Write down the definition first of all, and then substitute in what you can for function f. Now, in order for us to evaluate this, we actually need to expand this guy right here. X plus h to the 5th. And that's a binomial, and so you have a binomial theorem that we can use to expand that. All right, and definitely you want to use that formula because it'll make this go a lot faster. So let me demonstrate how we can do that just to refresh your memory. And then we'll come back to this problem here. This is the binomial theorem. When we expand this binomial, raise it to the fifth power, we're actually going to get 6 terms. There's going to be one more term than the power. And then the second thing that I need to know is what are the coefficients of those 6 terms going to be? Know that there's going to be 6 terms, what are the coefficients? And there are several ways that you can do that. I'm going to just show you one way with using Pascal's triangle. And Pascal's triangle says the following. So Pascal's triangle looks something like this. Start out with ones like this, and then each row starts out with a 1, and then the next row is 1, 2, 1 here. And the way that I know it's 1, 2, 1 is because I add the 1 and the 1 together to get me the 2. The next row, again, it starts with 1, and then it's a 3, 3, 1, and again, I know that is because 1 plus 2 gives me 3, 2 plus 1 gives me 3, and it begins with 1. And we continue doing this. 1, 4, 6, 4, 1, and so forth. We'll do one more of these. So we have 1, 5, 10, 10, 5, 1. And that's actually the row that we need. What these rows of Pascal's triangle show us are actually the coefficients for this expansion that we're about to do. In fact, if I were to write down that if I wanted to take something like, I'm going to put it in terms of a and b here. Well, actually, let's just use x and h. If I was going to take x plus h and raise it to the 0 power, anything of the 0 power, of course, is equal to 1. And so I would get just 1. The next row there, if I were to take x plus h and raise it to the first power, of course, anything to the first power is the same thing I started with, so that would just be 1x plus 1h. And if I were to take x plus h and raise it to the second power, I would get, of course, this, don't forget when you do that, you get a third term there, you get a middle term. You get x squared, you'd have 2xh, and you'd have a 1h squared. So those are the coefficients of that expansion, and so forth. So this is x plus h cubed, or the coefficients, I should say. This is the x plus h to the fourth, and then finally x plus h to the fifth. These are the coefficients when we expand them. Okay? So if I want to take x plus h and raise it to the fifth power, I now know how to find my exponents. And then the next thing I need to know is what are the actual terms going to be. And the way to do that is you just simply put a line there. The way to do that is just simply start out with x to the power that you're raising this to, and h to the 0 power. And as you go term by term, decrease the power of h and increase the power of, decrease the power of x and increase the power of h. So let me show you what that means. The coefficient for the first term is the 1 that I see right there from Pascal's triangle. And then I start out with x to the fifth, h to the 0. So I start out with x to the fifth power, the power I'm raising this to. This is x plus h to the fifth, sorry. And h to the 0. And then I add that to the next coefficient is the 5. And it's x to the fourth, h to the first. The next coefficient is the 10, x cubed, h squared. The next coefficient is 10, x squared, h cubed. Again, notice that I'm decreasing the powers on my x's, increasing the powers on h. Next coefficient is the 5, x to the first, h to the fourth, and then finally it's 1 times x to the 0, h to the fifth power. Now that's actually writing down everything. There's some things that we usually would not write down here. For example, coefficients of 1 are not necessary. H to the 0, that's just 1. Same with the very last term there, x to the 0, that's 1. Writing down h to the first, we just write that as h, and so forth. So when we do this, we get x to the fifth plus 5x to the fourth h plus 10x cubed h squared plus 10x squared h cubed plus 5x h to the fourth plus h to the fifth. That's how we'll write that down when we expand this. Okay? So let's go back to our problem here and continue on with this. This was kind of just a side note here of how we're going to do that expansion. And so we had f prime of x was equal to the limit as h goes to 0 of x plus h to the 5th minus x to the 5th all over h. And that's what we started out with here. And now let's substitute in. I know the x plus h to the 5th, we've just written that out actually. So this is the limit as h goes to 0 of x to the 5th plus 5x to the 4th h plus 10x cubed h squared plus 10x squared h cubed plus 5x h to the 4th plus h to the 5th. That right there is x plus h to the 5th. And I still have that minus x to the 5th. So minus x to the 5th still goes at the end, and this is all divided by h. Now, turns out that the stuff I'm subtracting here from the end in the numerator, in this case the x to the 5th, will cancel out with something here that I've just expanded. It's going to happen every time for you. Those will cancel out. And not only that, but if you look at what you have in your numerator, each term in the numerator has an h in it now. So let's factor out an h for each of the terms that are in the numerator. So I'll be left with 5x to the 4th when I factor out the h, plus 10x cubed h, plus 10x squared h squared, plus 5x h cubed, plus h to the 4th. And this is all divided by h. And here are my h's that will cancel out. That gets rid of that indeterminate form. Again, if you go back to what we started with, let me just scroll back up here real quick. If you were to plug in h as 0 here, realize that this takes on the form of x plus 0 to the 5th, that's x to the 5th minus x to the 5th, that's 0. Divided by h is going to 0, that's 0. That's that indeterminate form, just like we saw with the other definition of a derivative at a point. So I have to find something that's going to cancel out to get rid of that indeterminate form, which is what we just done here. And now I can actually evaluate this limit. So if I let h go to 0, I'll have 5x to the 4th. There's no h's in there, so in other words, it's kind of like a constant. Plus, the limit as h goes to 0, 10x cubed times h, that'd be 10x cubed times 0, which anything times 0, that's 0. The next term here is 10x squared times h squared, that's another 10x squared times 0, that's another 0 for us. 5x times h cubed, again h is going to 0, so that's another 0. And plus h to the 4th, again h is going to 0, so all those turn out to be zeros at the end. Normally we won't write all those zeros out, but just so you see we've evaluated each of those terms, I want to indicate that here. And so we end up with 5x to the 4th. Again, the significance of this is we're saying f prime of x is equal to 5x to the 4th. The derivative function is 5x to the 4th. If I wanted to find the derivative at 2, I can just simply plug in 2 now into this equation. If I want to find the derivative at 1, I just plug in 1 into that equation. So with one step, I've gone through the process here to find the derivative, but it's the derivative at every single point. A much better way to work with derivatives, because now I have the actual equation of that derivative function. All right. Now there are several properties that we need to know in order to work with derivatives and make this process actually go a little bit faster here for us. We'll see. The first one here is what we call our power rule, and in fact, if I look back at the problem that we just did, remember we started with x to the 5th, and the derivative turns out to be 5x to the 4th. So what we saw in the last section is it looks like when we take the derivatives of polynomials, we lose one in the power. That's what we see here, that we ended up with x to the 4th, rather than x to the 5th that we started with. But the other thing you'll notice is that we ended up with a 5 out front. So what used to be the exponent is now the coefficient out front, and we lost one in the power. That's actually our first property here, which is called the power rule. Power rule just simply says if f of x is equal to x to the nth power, then f prime of x is equal to n times x to the n minus 1. Makes it a very nice way, very quick way to find a derivative. I don't have to go through the whole limit process to find that derivative function. Here's the property we should have just noticed there from that last example. We're just simply generalizing that. So there's our power rule, used for finding the derivative of a power function. All right, and there are three other properties here that we need to talk about. The first one is for the derivative of a sum of functions. Now, if you recall, back in Chapter 2 when we talked about the limit theorems, there was a verbiage there that we used to describe those limit theorems. We said that the limit of a sum was equal to the sum of the limits. That same thing applies as we're going to go through these theorems right here. Derivative of a sum of functions, the derivative of a sum is equal to the sum of the derivatives. Okay? In other words, if I want to take the derivative of a sum of two functions, all I have to do is sum up the derivatives of the two functions. So the nice thing about that is that I don't have to worry about the whole function all at once. Just take the derivative term by term. If f of x is equal to g of x plus h of x, then f prime is equal to g prime plus h prime. So take it term by term. That's basically what that's saying. That's the first property. Let's take a look at the second property, which says for the derivative of a constant times a function, derivative of a constant times a function is equal to the constant times the derivative of the function. Again, the derivative of a constant times a function is equal to the constant times the derivative of the function. In other words, the constant just stays out front there. It's not, the derivative does not get rid of or change that value. It stays up front. So if f of x is equal to k times g of x, then f prime of x is equal to k times g prime of x. Constant just stays right up front. All right, let's take a look at one last property here. This is the one that I think we have seen many times now, or at least noticed many times now, but this is the derivative of a constant function. Remember, a constant function would be a horizontal line, and the slope of a horizontal line, which is what the derivative finds for us, the slope, is 0 everywhere. So this one shouldn't be too much of a surprise for us, that if f of x is equal to some constant k, then f prime of x is equal to 0. So the derivatives of constants basically disappear. They go to 0. All right, let's use those properties in a couple of examples here. Take a look at example 2. It says if f of x is equal to this function, f of x is 5x to the 7th minus 11x cubed plus 12x minus 47. Then f prime of x is equal to what? Find f prime of x is what they say. So we're just going to go through and use the properties that we've just learned to do this. You could again go back to that limit definition and actually evaluate it that way. We're going to use the properties that we just learned. So the first thing that I should notice is that I've actually got a sum of 4 functions here. I'm going to use that sum property. And the sum property says the limit of a sum is equal to the sum, or excuse me, the derivative of a sum is equal to the sum of the derivatives. So I can take each derivative individually and then add all those up, in other words. So let's focus on the first one here, 5x to the 7th. I've got a constant, 5, times a function, x to the 7th. And my rule for the derivative of a constant times a function was the constant stays out front. So the derivative is 5 times the derivative of my function, which my function in this case is a power function, x to the 7th. And my rule for the derivative of a power function, the 7 comes out front, times x raised to, and we subtract 1 from our exponent, so it's x to the 6th. So it's 5 times 7x to the 6th. And then I add, or in this case I'm subtracting, the derivative of the next function. So again, I've got a constant times a function, so the constant stays up front, so it's a minus 11 times. times the derivative of my function, which my function is another power function, so follow your power rule. The 3 comes out front, times x raised to, and you subtract 1 from the exponent to get x squared. And then we add that to the next function. That's another constant, 12, times my function x. So our rule is the 12 stays out front, times the derivative of my function. Now, if you want to, think of this as being x to the first. I'll put a little 1 there to indicate it's x to the first. If it helps you to write it that way, go ahead and do so. So the derivative of that, of course, using your power rule, is 1 times x to the 0 power. The 1 comes out front, the exponent comes out front, and you subtract 1 from your exponent to get 0. And then finally, at the end, minus the derivative of 47. 47 is a constant, so we said the derivative of constants are 0. And now let's just kind of combine these coefficients so it makes it look a little bit nicer. 5 times 7 is 35, x to the 6th. 3 times 11, that's 33, minus 33, x squared. Now 1 times x to the 0. X to the 0 is just 1. 1 times that, of course, is just 1. So we end up with just 12 there. Notice that when you have a linear term, 12x, it's linear. The derivative is just the 12, which makes sense since the derivative is the slope. The slope of the linear function is, of course, the coefficient out front. There's our derivative function. All right, that is the end of this section here for us. So let's, we'll end right now.